Hello, dear friends, dear students. Once again, I am here, Lti Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Dear students, I came here with the subject digital signal processing. Already we have studied near about all the units of the digital signal processing in the last videos and lectures, even in the classes also before this lockdown period. But now I am interested to tell you something about this, more things about this linear time invariant systems. That's why once again I am dealing with this linear time invariant system, which is part of unit 1 and unit 2 and in general also for the DSP. And it is very useful for the analysis of the systems. And hence we will go through this linear time invariant system to carefully listen and understand these linear time systems for the digital signal processing as well as signals and system also for analyzing the systems and signals. Let us see now. Here you can observe, dear students, this is discrete time system. Input and output description of systems are given here. The input and output description of discrete time system consists of a mathematical expression which defines the relation between input-output signals. So my dear students, I am going to discuss some relations, mathematical relations which uses in digital signal systems and describe certain characteristics. Let us see. This is the input supposed to be, and here you assume that in digital systems, that is in discrete time system also, the input is in terms of the discrete time signal, that is x of n, not x of t. It is discrete time signal. So let us suppose to be this is input signal x of n, or this is called as a excitation applied to the DTS, discrete time system, and y of n is supposed to be output signal response. Now within this discrete time system, any of the transformation, any of the relation described in the problem or system may be here. Let us see now the various types of relations used in discrete time systems or digital discrete time systems or digital signal processing. For examples, this is called as pass-through relation, where y of n is equal to the x of n, output is equal to the input. Just like in our analog system, all pass filter is there. Similarly, this is pass through in case of the discrete time system. Then this is unit delay represented by x of n minus 1. Y of n is equal to x of n minus 1. In terms of z transform, we represent this as a z inverse x of z. If it is delay by 2 samples, it may be represent z to the power minus 2 x of z. Then amplified by a factor of 2. Then y of n is equal to 2 into x of n. Just you can say this is gain. Gain delays with a gain. This is x of n minus 2, that is delay by 2 sample and amplified by a factor of 3. This is called as gain. Gain delay. It is called as a gain delay, this relation. Then moving average. This is given by y of n is equal to 1 by 3 let us say 3 values are here, that is x of n minus 1 plus x of n plus x of n plus 1. Average of three parameters is the y of n. This is called as an averager, moving average. Then weighted summations. Supposed to be this is delay by one sample divided by 2. This is current sample divided by 4. And this is advanced sample by one sample divided by 3. So this is called as a weighted. This is weighted sample by 2. This is weighted sample by 4. This is advanced sample by 3 or weighted sample by 3. So this individual weight of the signal is available here. This is called as weighted summation. Absolute value. Just like in mathematics we represent in terms of the magnitude, similarly in discrete time system we represent y of n is equal to magnitude of x of n. Then squares, y of n is equal to x of n whole square. Then max filters. Max filters are given by the relation y of n is equal to max of x of n minus 1, x of n, x of n plus 1. Whatever is the maximum will be considered. This is called as a max filter. Then accumulators. It is a summation. Y of n is equal to summation k is equal to minus infinity to n x of k. This relation is very important in digital signal processing because it also uses in the convolution and the FIR filters also. Later on, again, moving with the relations, we have the moving averages like y of minus 1, that is delay output by at one sample. Not delay, you can say it is a behind, that is minus 1. 1 by 3 x of minus 2 plus x of minus 1 plus x of 0. Y of 0 is equal to 1 by 3 x of into 1 x of minus 1 plus x of 0 plus x of 1. Y of 1 is equal to 1 by 3 into x of 0 plus x of 1 plus x of 2. And this is the relation y of 3 is equal to 1 by 3 x of n minus 1 plus x of n plus x of n minus 1. And you can see this diagram here which is shown. This y of minus 1 is the summation of this x of minus 2, x of minus 1 and this x of 0. Y of 0 is the summation of these three arrows are shown here. This one and this one. Again y of 1 is the average of these three. Summation of these three, x of 0, x of 1 and x of 2. So this type of situations or systems are used in the digital signal processing. Again, some relations. Systems may use present inputs, that is depending on x of n only. This is y of n is equal to x of n. And any relations which uses the y of n having the value of x of n are called as the present inputs. Then and are past inputs, x of n minus 1, x of n minus 2, x of n minus 3. These are called as the past inputs. So output is dependent on the past input. Here output is dependent on the present input. And are future inputs. Here you can see x of n plus 1 is there. So this is the future input. So this y of n is the average of these three. Past value x of n minus 1, present value x of n and future value x of n plus 1. So this is the combination of all past, present and future. Similarly, to produce the present outputs, you can have any type of relation, such type. This is called as weighted functions, and weighted functions are added here. Any type of discrete time system have the relations. or even previous outputs to produce the present outputs like this. This is the y of n minus 1 is the present output, while y of n minus 2 is the previous output, and x of n is the present input. So this type of relation between input and output may also be studied in future of this digital signal processing units. Quick review of LTI system. You can say LTI systems are uniquely determined by their impulse response. Impulse response is del of n. Impulse function is del of n, and the response is given by the h of n. Response of the impulse function is always given by h of n. So here let us say y of n is equal to summation k is equal to minus infinity to infinity x of k h of n minus k. This relation is called as the convolution, and this convolution is very important in digital signal processing, and this convolution is given by this equation. Particularly convolution function is abbreviated by x of k star h of k. It is not multiplication. Star is written here. Star indicates the convolution in discrete time system or digital signal processing. So x of k star h of k. So it is a convolution which is given by this equation. It is not multiplication. And this is a very powerful tool in digital signal processing called as the linear convolution. Now we can write the input-output relation also in the form of Z transform. Any transfer function of the filter can be written in terms of the Z transform, that is h of z, and h of z is equal to y of z upon x of z. So this is called as Z transform. Any of the digital filter, whether it is IIR filter or FIR filter, it can be represented with a transfer function h of z called as the digital filter. And digital filters are always in terms of Z transform, while in case of the analog filter we represent by the Laplace transform, and there is a relation between Laplace and Z transform also. So here output in Z transform y of z is equal to h of z is the transfer function, x of z is the input. So this can be represented in Z transform, and hence Z transform plays a very important role in case of the digital signal processing. Or we can define an LTI system with the frequency spectrum or frequency response y of e to the power j omega is equal to h into e to the power j omega into x of e to the power j omega. You can see the relation between Z transform and this frequency transform. Or I can say this equation may be in terms of the Fourier transform, where omega is the frequency, and hence Z transform, there is a relation between Z transform and Fourier transform also. Z is equal to e to the power j omega we can put here, and we can obtain the Fourier transform. Whether the Fourier transform exists or not, we have a Dirichlet condition for observing the Fourier transform. H of e to the power j omega defines magnitude and phase change at each frequency. Why we need this Fourier transform? Because we have to study the phase spectrum as well as the magnitude spectrum, and that's why we need this Fourier transform. Then we can define a magnitude response and a phase response. You can calculate the magnitude of this y of e to the power j omega is equal to magnitude of h of e to the power j omega into magnitude of x of e to the power j omega. Similarly, angle you can calculate. Angle of y of omega is equal to phase of h of e to the power j omega plus phase of x of e to the power j omega. Since multiplication is there, while calculating the phase, we must add here a separate phase of the components. Now, the frequency response. The frequency domain representation of LTI system. The Fourier transform representation is the most useful signal representation for LTI systems. It is due to the following results. Response to the complex exponential e to the power j omega n, that is called as Fourier. Response to the sinusoidal sequences and response to the arbitrary sequences. These are important in digital signal processing. The frequency response to the complex exponential can be obtained e to the power j omega 0 n is applied to the h of e to the power j omega. This is transfer function, and you will get here h of e to the power j omega into e to the power j omega n. We will get the magnitude here and we will get the phase response here. This is called as frequency response. The output sequence is the input exponential sequence modified by the response of the system at frequency omega naught. Response to sinusoidal sequences, like supposed to be the sinusoidal sequence is given by x of n is equal to a cos omega 0 n plus theta naught, and y of is equal to a magnitude of h of e to the power j omega 0 cos of omega 0 n plus theta 0 plus angle h into e to the power omega 0. So these are the very basic things used in the digital signal processing from unit number 1 to last unit. That's why I understand that this should be once again you get it in proper way. In next video we will continue for this linear time invariant system and basics of the digital signal processing also. This is very, very important. So my dear students, please go through today's video. Later on we will continue this another video with respect to this one, frequency response, and other many more things which I have included here. So we will go later on in next videos. Thank you very much. Thank you very much. And if you have any difficulty, you can ask me. We will continue later on. And you can ask me any difficulty at any platform, please. Thank you very much.